spring, there's not really an H in the word spring, but spring energy. All right, so what's up with the energy in a spring? Well, you have done a little bit of lab work at this point, so you know that a lot of springs, not all of them, some of them we call linear springs. And that's the same as for a linear spring. That's the same as saying that we have a spring that obeys Hooke's law. And what is Hooke's law? That is that spring force is equal to some constant K. We call this the spring constant. Why do we use K? I really have no idea why we chose K there. Maybe because constant. Maybe because I think if you write the word constant in German, I'm pretty sure it starts with a K. But there's other constants out there, obviously, so why would the spring get that? I don't know. But it's always a K since forever that I've seen it. So spring force is equal to Kx. And that, if you made a graph, of spring force versus x like you did in the lab, it's going to look like this. The slope of that is k. So it's a linear spring. There's the line. You know, there's nothing super surprising about that. We do want to actually say here, we want to be careful that we understand that there really should be a negative sign here. Why? Because the spring force and the displacement are going to always be opposite to each other. So in other words, if you have a spring and it gets compressed a little bit, then, so I'm pushing here this way, right? So the displacement of it, the x, would be this way. What direction is the spring pushing? The spring force. It's pushing back the other way. We don't want to confuse the spring force for the force that's either compressing. Like, you don't want to confuse the spring force with the McGrath force, which is compressing the spring. We're talking about the force exerted by the spring. Now, of course, if there's a force of spring on McGrath's hand, then there's a equal opposite force of McGrath's hand on spring. Everything comes in those third law pairs. The negative sign you could think of as reminding us that spring force is a restoring force. So right now that spring is in equilibrium. If it gets stretched out a little bit, it wants to go back. If it gets compressed a little bit, it wants to go back. So whatever displacement it's experiencing, the force is the opposite direction because it wants to go back to equilibrium. So that's another little note that we should say. This x here, you do not get to just pick whatever origin you want for this x like we do when we're doing just general motion problems. Here, this x is displacement from equilibrium. Right? What does equilibrium mean? That means when there's no spring force. That's like the relaxed spring. So right now there's no delta x. Now there's a delta x this way, so the force is this way, and then vice versa, and all that. Okay, so how about now the work done by a spring? Well, so here's some thoughts. In general, work is equal to force times distance times cosine of the angle between them. Here we're talking about, this is all like one-dimensional kind of motion we're talking about, so that's not really going to be at play. But actually I can't use this at all because this is This only works if for constant forces. Sorry, that should say constant force. That should be the other way around. You get the idea. So what do we do here? Well, we're going to go with the idea that here, the reason, or one way of understanding this force times displacement, if we have some constant force here, and we have some displacement d, that multiplying force times distance is area. So the area still works here. So for variable force, I don't really like that so there. I don't think that logically belongs there. So for variable force, the work done is still the area. That, we actually have a way of writing that now. We can use calculus symbols to do that. So work is equal to the integral from some displacement, some position to some other position of the force dx. In other words, it's the area. That's our nice symbolic, compact way of saying it's the area under the force versus x curve. And if you're looking for reasons why that dx has to be there, like in calculus class or here, it's super important here, and maybe helps us understand why we always have to have that, whether we're doing calculus or physics or whatever, because this needs to be a force versus displacement or position graph. If this was a force versus time graph, we couldn't figure out work from that. The work would not be the area under that. It has to be force in x, right? Because work is equal to force times distance. So we have to have that distance, and this is telling us that, yes, dx, that's the variable here, right? Because you could have a force versus time graph. In fact, in Chapter 9, we're going to look at what a force versus time graph can tell us. So there you go. Okay, so if that's true, then what's the area here? And I want you to just note here that although I wrote this force, this is like the magnitude of that, right? I didn't make this negative like that, with that negative sign. I just drew probably like what you did in the lab. You just said, okay, there's this much force. That's the magnitude of the force and this much displacement. So you didn't get a negative slope, and that's fine. But here, since we're talking about work, and work can be positive or negative, we do have to be careful about that. So I'm going to redraw. Here's my force versus x graph, and here is my line. That is force equals negative kx. And let's say we have some displacement here. So let's say we want to know how much work is done by the spring when it goes from here to here. Well, that would be the area of this triangle. Now it's underneath, so that's going to be negative. Okay, let's think about that for a second. Does it make sense that if the spring goes from here, that's its equilibrium position, to some positive here, that there should be negative work done by the spring? Yes, it does, because the spring is pulling that way and the displacement is this way. So yes, that makes sense that it would be negative work. If there's kinetic energy to be changed, then definitely if something like was moving along this way and like caught the spring, then the spring would slow it down. It would remove kinetic energy, do negative work. Okay, so what's the area of this little triangle here? Well, let's see. That's 1/2 base times height. So let's see. The base here would be x. So 1/2 base. And then this would be like f, but f is equal to negative kx, right? So if I've gone over x, then this is like negative kx. So that's negative 1/2 kx squared. And that is pretty much all that you need to know about the work done by a spring. Yeah, I think that's it. If you're moving from one, that's from 0. So if you're moving from, which is often what we're doing, this is from 0. In general, the work done by a spring is equal to negative 1/2 kx final squared minus 1/2 kx initial squared in general. And then, of course, if kx initial, if x initial is 0, that goes away, and you just get this. Now, you might be wondering to yourself, why would you write it like with a negative sign out here and then another negative sign? Why wouldn't you just like distribute that and have the initial minus final? I am happier writing it this way because it has the final minus initial, right? So you could say that it's like negative delta. We're gonna, I don't think this is too much of a spoiler alert, but we are going to assign the spring potential energy is going to be equal to this. So it's going to be equal to negative delta spring energy. Let's just say that for now. And we'll define that better in Chapter 8. But for now, I like final minus initial. That goes along with our sense of delta things. So it's negative delta 1/2 kx squared. All right. So there you go. Fun with springs. Boing. Want to hear a joke? I just reminded myself of one of my favorite jokes of all time. What is brown and sounds like a bell? Dung.